On this quiet night, when everything around you has grown still and the sky is scattered with countless stars, pause for just a moment and wonder how old their light might be. Some of those rays have been traveling for millions of years, others for billions, moving slowly through the deep vastness of space just to arrive here, now, in this very moment. We have studied distant galaxies, mapped galaxies across vast stretches of space. We have calculated the age of the universe with remarkable precision. We have even detected the faint afterglow of its earliest moments, a subtle radiation that still fills the cosmos like a lingering whisper from the beginning of time. And yet, for all this progress, something extraordinary remains unresolved. When astronomers carefully observe how galaxies move, they notice something that does not quite fit. Galaxies spin, their stars orbiting around bright central regions. According to the gravity produced by the visible matter alone, the stars, gas, and dust we can detect, the outer stars should move more slowly than those near the center. That is how gravity behaves in systems we understand, like our own solar system. But that is not what we see. The stars at the edges of galaxies move far faster than expected, fast enough that by our usual calculations they should escape into deep space. And yet they do not. They remain bound, circling steadily as if held in place by an unseen hand. This pattern appears again and again in galaxy after galaxy. It suggests that what we see, all the luminous matter glowing against the dark, is only part of the story. Surrounding each galaxy seems to be a vast, invisible halo of mass. It does not shine. It does not absorb light. It cannot be seen directly by any telescope. And yet, its gravitational pull is unmistakable. We call this hidden substance dark matter, not because it is sinister, but because it is invisible to light. It outweighs all the ordinary matter in the universe by a wide margin. In fact, most of the matter in the universe appears to be this unseen form. And as we continue drifting deeper into this mystery, we begin to realize that the universe we can see may only be a thin surface layer, resting upon something far greater and far more elusive than we ever imagined.
If dark matter truly surrounds every galaxy like an invisible ocean, then we are living inside it even now. As you rest here, calm and unmoving, countless particles of this unknown substance may be passing silently through your body, through the walls around you, through the entire Earth itself. They leave no trace. They make no sound. Their presence is revealed only by the quiet pull they exert on the cosmos. The idea began to take shape nearly a century ago when astronomers turned their attention to galaxy clusters, enormous collections of hundreds or even thousands of galaxies bound together by gravity. When scientists measured how fast those galaxies were moving within the clusters, something did not add up. The galaxies were traveling far too quickly. Based only on the visible matter, the stars, gas, and dust, the clusters should not have been stable. They should have drifted apart over cosmic time, and yet they remained intact. At first, many assumed the measurements were incomplete. Perhaps there was more ordinary matter than could be seen. But as instruments improved and observations multiplied, the same discrepancy appeared again and again. Individual galaxies showed the same strange behavior. Their outer stars orbited at nearly the same speed as inner stars, defying expectations set by classical gravity. It was as though each galaxy were embedded in a vast, unseen halo of mass. One of the most powerful confirmations came from a subtle and beautiful effect known as gravitational lensing. According to Einstein's description of gravity, massive objects curve space itself. When light passes through that curved space, its path bends. Galaxy clusters, then, can act like enormous cosmic lenses, warping the light from even more distant galaxies behind them. By carefully analyzing these distortions, astronomers can map the distribution of mass within a cluster, even if that mass emits no light, and the results were unmistakable. The majority of the mass did not align with the glowing gas and stars. Instead, it formed broad, invisible regions extending far beyond what telescopes could directly detect. In one particularly striking observation of two merging clusters, the hot gas, which makes up most of the visible matter, collided and slowed down, but the main concentration of gravitational mass passed straight through, as if unaffected. This suggested that the dominant matter component interacts very little, if at all, except through gravity. These quiet clues point toward a profound conclusion. Most of the matter in the universe is dark, unseen, elusive, and fundamentally different from the atoms that form stars, planets, and ourselves. And as we continue, the question gently shifts from whether dark matter exists to what exactly it might be.
As the evidence for dark matter grew stronger, the focus slowly shifted from observation to identity. If this unseen substance truly outweighs all ordinary matter, then what is it made of? What kind of particle or phenomenon could move silently through the universe, shaping galaxies without ever revealing itself to light? For many years, one of the leading ideas centered on something called a weakly interacting massive particle, often shortened to WIMP. These hypothetical particles would have mass, which means they would exert gravity. But they would interact only through the weak nuclear force and gravity, avoiding the electromagnetic force entirely. That would explain why they neither emit nor absorb light. They would be invisible by nature. The possibility was elegant. In fact, certain extensions of particle physics naturally predicted particles with just these properties. If WIMPs existed, they might occasionally collide with ordinary atoms, producing a tiny flash of energy. To search for these rare interactions, scientists built exquisitely sensitive detectors deep underground, shielded beneath layers of rock to protect them from cosmic rays and background noise. These experiments waited patiently, year after year, for a faint signal, a subtle vibration, a whisper of energy, anything that might suggest a dark matter particle had brushed against an atomic nucleus. But so far, the silence has persisted. As one experiment after another reported no confirmed detection, researchers began widening their search. Perhaps dark matter is not heavy at all. Another compelling candidate is a particle known as the axion. Unlike WIMPs, axions would be extraordinarily light, almost ghost-like, yet so abundant that together they could account for the missing mass. Special experiments now attempt to detect them by converting these faint particles into measurable photons within strong magnetic fields. Other possibilities stretch even further. Some propose sterile neutrinos, particles that barely interact with anything. Others suggest entire hidden sectors of physics, complete with their own forces and interactions. There is even speculation that dark matter could consist of primordial black holes formed in the earliest moments of the universe. And still, another possibility lingers quietly in the background. What if dark matter is not matter at all? What if our understanding of gravity itself
changes on cosmic scales. Modified gravity theories attempt to explain galactic motion without invoking unseen mass. Yet so far, none fully account for all the evidence as cleanly as dark matter does. So, the mystery remains open. We can measure how much dark matter there must be. We can trace its gravitational influence across billions of light years. We can simulate its role in shaping cosmic structure. But its true nature, its essence, continues to elude us. And as we move deeper into this quiet exploration, the mystery becomes less about missing particles and more about the limits of what we truly understand about the universe itself.
To understand why dark matter matters so deeply, we have to drift back in time, far beyond stars, beyond galaxies, back toward the earliest chapters of the universe itself. In those first moments after the Big Bang, the universe was unimaginably hot and dense. Matter and radiation were tightly intertwined in a brilliant, glowing plasma. Ordinary particles, the protons and electrons that would one day form atoms, were constantly interacting with light. Photons scattered off charged particles, keeping everything mixed and preventing matter from clumping together. In that early era, structure could not easily form. Gravity was present, of course, but radiation pressure resisted collapse. The young universe was smooth, almost uniform, with only tiny fluctuations in density, slight variations in how matter was distributed from place to place. But dark matter, if it existed then as it does now, would have behaved differently. Because it does not interact with light, it would not have been slowed or stirred by radiation. While ordinary matter remained locked in its glowing dance with photons, dark matter could begin gathering quietly under gravity's pull. It would have formed invisible concentrations, gentle wells in the fabric of space. As the universe expanded and cooled, something remarkable happened. About 380,000 years after the beginning, temperatures dropped enough for electrons and protons to combine into neutral atoms. Light was finally free to travel without constant scattering. The universe became transparent. That ancient light still fills space today as the cosmic microwave background, a faint afterglow of the early cosmos. By that time, dark matter's gravitational scaffolding was already in place. The tiny density fluctuations in dark matter had grown slightly denser over time. When ordinary matter was finally free to move without radiation pressure, it began falling into those pre-existing wells. Gas flowed inward, regions became denser. Over millions of years, the first stars ignited. Over billions, galaxies assembled, tracing out vast filaments and clusters across space. Computer simulations help us visualize this process. When dark matter is included, the simulated universe forms a cosmic web, long strands connecting dense nodes, separated by enormous voids. This structure closely resembles what we actually observe when we map galaxies across the sky. Without dark matter in those simulations, the universe looks dramatically different. The large-scale structure simply does not form in the same way. In this sense, dark matter is not just an add-on to our models, it is foundational. It acts as the hidden architecture upon which luminous matter organizes itself. The stars you see above tonight, the galaxies scattered across the darkness, may exist because of something that never shines. An unseen framework that quietly shaped the cosmos long before the first atoms settled into place. And just as we begin to appreciate this invisible scaffolding, another mystery emerges,
one that does not pull inward like gravity, but pushes outward instead. As if the quiet dominance of dark matter were not mysterious enough, the universe holds another surprise, one that moves in the opposite direction of gravity. For much of the 20th century, astronomers assumed that the expansion of the universe, set in motion by the Big Bang, must be slowing down. Gravity pulls matter together. Galaxies attract one another. Over time, that mutual attraction should gradually reduce the rate at which space stretches. The key question was never whether expansion would slow, only by how much. To measure this cosmic deceleration, astronomers studied distant exploding stars known as Type 1a supernovae. These brilliant events occur when a dense white dwarf star gathers matter from a companion until it reaches a critical limit and detonates. Because these explosions happen under nearly identical conditions, they shine with almost uniform brightness. That makes them reliable, standard candles. By comparing how bright they appear to how bright they truly are, scientists can calculate their distance with remarkable precision. In the late 1990s, two independent research teams set out to chart how the universe's expansion had changed over time. They observed supernovae billions of light years away, expecting to see evidence that expansion had slowed down. Instead, they found something astonishing. The distant supernovae were dimmer than expected. That meant they were farther away than predicted. The universe had not been slowing down, it had been accelerating. Rather than gravity gradually pulling everything inward, something else seemed to be pushing space outward, and doing so more strongly as time passed. This discovery reshaped cosmology almost overnight. To describe this mysterious influence, scientists revived an old idea, the cosmological constant. Originally introduced by Einstein and later abandoned, it represented a uniform energy density inherent to space itself. In modern terms, this phenomenon became known more broadly as dark energy. Unlike dark matter, which gathers and forms halos around galaxies, dark energy appears smooth and evenly distributed. It does not clump, it does not form structures. Instead, it exerts a subtle negative pressure, causing space to expand at an ever-increasing rate. Today, observations suggest that dark energy makes up roughly 2/3 of the total energy content of the universe. Dark matter accounts for most of the rest. Ordinary matter, the stars, planets, oceans, and living beings, represents only a small fraction of the whole. Over billions of years, dark energy has gradually overtaken matter as the dominant influence on cosmic evolution. Galaxies are drifting farther apart. Distant regions of space are receding faster and faster. In the far future, some galaxies may move beyond the reach of light itself, slipping permanently out of view. And so, the picture becomes even stranger. Not only is most of the universe made of something invisible, it is also driven by something that quietly stretches the fabric of space, guiding the fate of everything that exists. The discovery of cosmic acceleration left scientists with a profound question. What exactly is dark energy? Is it truly a constant property of space, unchanging and uniform? Or is it something more dynamic, a field that evolves over time, subtly shifting the destiny of the universe? If dark energy is simply the energy of empty space itself, then even the vacuum is not truly empty. In quantum physics, What we call empty space is never perfectly still. Tiny fluctuations constantly occur. Particle-antiparticle pairs appear and vanish in fleeting moments. These quantum ripples suggest that the vacuum carries energy. In theory, that vacuum energy could behave just like the cosmological constant, exerting a steady outward push on space. But when physicists attempt to calculate how much energy the vacuum should contain, the numbers become astonishing. The predicted value is vastly larger than what we observe. The difference is so extreme that it has been called one of the greatest mismatches between theory and observation in all of science. Why is the observed value of dark energy so small? Why is it not zero? And why does it happen to be comparable in magnitude to the current density of matter precisely at this moment in cosmic history? These are questions without clear answers. Some researchers explore alternatives known as dynamic dark energy models. In these ideas, dark energy is not fixed but changes slowly over time. It may behave like a gentle field permeating space, gradually shifting its strength as the universe evolves. If that were true, the long-term future of the cosmos could look very different depending on how this field behaves. In one possible scenario, expansion continues forever, galaxies drifting farther apart until the night sky grows dark and empty. In another, if dark energy strengthens over time, it could eventually overcome all forces, pulling galaxies, stars, and even atoms apart in a distant event, sometimes described as a cosmic rip. And in yet another possibility, dark energy might weaken, allowing gravity to regain dominance. At present, observations suggest that dark energy behaves very much like a constant, but the measurements are delicate. Astronomers continue refining their data using supernovae, galaxy surveys, and subtle distortions in light caused by gravitational lensing. Each new dataset tightens the constraints, narrowing the range of possibilities. What makes dark energy so unsettling is not just its dominance, but its subtlety. It does not announce itself through dramatic explosions or bright signals. Its influence is revealed only through careful measurement of vast cosmic distances and timescales. As you rest here tonight, it may seem impossible that space itself is stretching faster and faster. And yet, on scales far beyond everyday experience, that quiet expansion is shaping the future of every galaxy in existence, including our own. When we place dark matter and dark energy side by side, a curious symmetry appears. One pulls inward, helping galaxies form and remain intact. The other pushes outward, steadily increasing the expansion of space. Together, they shape the large-scale story of the cosmos. One building structure, the other gradually separating it. And yet, both remain unseen. If you could zoom out far enough, beyond our Milky Way, beyond neighboring galaxies, beyond even the largest clusters, you would see a vast cosmic web. Galaxies are not scattered randomly. They trace delicate filaments stretching across hundreds of millions of light years, intersecting at dense nodes and surrounding immense voids of nearly empty space. This web-like structure reflects the early imprint of dark matter's gravitational scaffolding. Over billions of years, matter gathered along those invisible threads. Gas cooled, stars ignited, galaxies merged and evolved. But as dark energy slowly gained dominance, the expansion between these large structures accelerated. The web stopped growing as quickly. Clusters became more isolated. The large-scale architecture of the universe began to freeze in place. Today, we live in a transitional era. Matter no longer dominates cosmic expansion, yet its structures remain intact. Dark energy drives acceleration, but its influence has only recently overtaken gravity on the largest scales. In a sense, we are observing the universe at a uniquely balanced moment, late enough to see galaxies fully formed, yet early enough that they have not drifted beyond view. In the far future, the night sky may look very different. As expansion continues, distant galaxies will move beyond the cosmic horizon, the distance beyond which light can no longer reach us. Over immense timescales, observers in our galaxy might see only their local group of stars, unaware of the vast universe that once surrounded them. This possibility reshapes how we think about knowledge itself. The universe reveals its history through light that takes time to travel. But if acceleration continues indefinitely, future civilizations may lack access to the evidence we now study so carefully. The cosmic microwave background, distant galaxies, the large-scale web. Their observable universe would be smaller, quieter, more isolated. But for now, though, we are fortunate. We can detect the faint afterglow of the early universe. We can measure galaxy distributions across immense distances. We can observe supernovae billions of light years away. Each observation acts like a soft echo from the past, carrying clues about invisible components that dominate reality. And perhaps that is the most humbling realization of all. Everything familiar, the atoms in your body, the earth beneath you, the stars overhead, represents only a small fraction of what exists. The majority of the universe is composed of something we cannot see and barely understand. Yet, through patience, mathematics, and careful observation, we continue to trace its outline, quietly, gently, one mystery at a time. As our measurements grow more precise, another quiet tension has begun to emerge, a subtle disagreement in the universe's expansion rate itself. Astronomers determine how fast the universe is expanding using two primary methods. One looks far back in time, studying the cosmic microwave background, the faint afterglow of the early universe. By analyzing tiny fluctuations in that ancient light, scientists can infer the expansion rate with extraordinary accuracy. The other method looks closer to home, measuring distances to nearby galaxies using standard candles like Cepheid variable stars and Type 1a supernovae. By observing how fast these galaxies are moving away from us today, researchers calculate the current expansion rate directly. In principle, both methods should agree. They are measuring the same universe, after all, just at different stages of its history. But they do not quite match. The expansion rate derived from the early universe appears slightly slower than the rate measured from nearby galaxies. The difference is small, yet persistent. It has survived improvements in instruments and analysis. This discrepancy is known as the Hubble tension. No one yet knows whether this tension points to hidden systematic errors or to something deeper. It may hint that dark energy is not perfectly constant. It may suggest new particles that subtly altered early cosmic conditions. It might even imply that our understanding of gravity requires refinement. What makes this tension fascinating is its gentleness. There is no dramatic signal, no sudden anomaly, just a quiet mismatch in numbers echoing across billions of years. And yet within that mismatch may lie clues to new physics. Perhaps dark matter interacts slightly differently than assumed. Perhaps dark energy evolves over time. Perhaps additional fields or particles influenced the early universe in ways we have not yet accounted for. Science often advances through such small inconsistencies. A deviation in Mercury's orbit once hinted at general relativity. Tiny irregularities in atomic spectra led to quantum mechanics. Sometimes a minor discrepancy opens the door to a profound shift in understanding. As you rest here tonight, it may be comforting to know that the universe still contains unanswered questions, not because we lack knowledge, but because discovery is ongoing. Each measurement refines our map of reality, revealing edges we did not know existed. The cosmos is not a finished puzzle, it is a living investigation. Dark matter shapes galaxies, dark energy stretches space, and subtle tensions in expansion whisper that something even deeper may be waiting beneath the surface. We are not at the end of understanding. We are somewhere in the middle, gently uncovering a reality far more intricate than it first appeared.
As the questions grow more subtle, so do the tools we use to explore them. To study something that cannot be seen directly requires extraordinary patience and creativity. Over the past few decades, scientists have designed experiments that are almost unimaginably sensitive, instruments capable of detecting the faintest tremors of energy. Deep underground, beneath mountains and old mines, detectors sit in near-perfect silence. They are shielded from cosmic rays and background radiation, cooled to temperatures close to absolute zero. Within them are crystals, noble gases, superconducting materials, each waiting for the rare possibility that a dark matter particle might pass through and gently collide with an atom. The hope is simple, that one tiny interaction might produce a measurable flash of light, a minuscule vibration, or a small release of energy. But so far, the results remain quiet. The detectors continue listening. Other experiments look not underground, but outward. Particle accelerators attempt to create dark matter in high-energy collisions, searching for missing energy that might signal invisible particles slipping away. Space telescopes scan the centers of galaxies for unusual gamma-ray emissions that could arise if dark matter particles annihilate each other. Radio observatories tune in to narrow frequency bands, listening for faint conversions of hypothetical ultralight particles. Each approach is different. Each probes a different range of mass, interaction strength, or behavior. Together, they form a wide net cast across the unknown. At the same time, astronomical surveys are mapping the universe with increasing precision. New telescopes chart billions of galaxies, tracing how matter clusters across vast distances. Subtle distortions in the shapes of distant galaxies caused by gravitational lensing reveal how dark matter is distributed on cosmic scales. These maps help refine models and narrow possibilities. Yet, despite this effort, direct confirmation remains elusive. This does not mean failure. Science often moves through long periods of refinement. Each null result constrains theories, ruling out possibilities and guiding attention elsewhere. The parameter space, the range of masses and interaction strengths that dark matter could have, becomes narrower and more defined. Perhaps dark matter is lighter than once imagined. Perhaps it interacts through forces we have yet to discover.
Perhaps it exists as a field permeating space rather than as discrete particles. Or perhaps the solution lies somewhere entirely unexpected. What is remarkable is not that we have unanswered questions, but that we can frame them so precisely. We know how much dark matter must exist. We know how it behaves gravitationally. We can simulate its influence from the earliest moments of time until now. We stand at the edge of understanding, equipped with instruments of astonishing sensitivity, listening carefully to the quiet universe. And in that stillness, the mystery remains, not as a barrier, but as an invitation to look deeper.
As our instruments become more refined, another possibility begins to feel less speculative and more intriguing. What if dark matter is not a single substance at all? After all, ordinary matter is not simple. It is made of quarks and electrons, bound together into atoms, which form molecules, which build stars and planets. It interacts through multiple forces. It clumps, radiates, cools, and evolves. If the visible universe is so rich and layered, why assume the unseen majority is uniform? Some theorists now explore the idea that dark matter might consist of multiple components. There could be heavier particles and lighter ones. Some might interact weakly with each other, forming subtle structures. Others might pass through everything without resistance. In certain models, dark matter even possesses its own hidden forces, a shadow version of electromagnetism operating in a sector invisible to us. If that were true, the dark universe could be far more complex than we imagine. There might be dark atoms, dark radiation, even dark chemistry unfolding silently alongside our own cosmic history. These ideas remain speculative, but they are not arbitrary. They arise naturally when physicists extend existing frameworks of particle theory. The mathematics allows for hidden sectors, collections of particles that barely interact with familiar matter except through gravity. At the same time, some researchers revisit a more radical possibility. Perhaps gravity itself behaves differently on enormous scales. Instead of unseen mass, maybe the laws governing motion and curvature require adjustment. Modified gravity theories attempt to reproduce galactic rotation curves without invoking dark matter particles. Yet these alternatives face challenges. While they can sometimes explain individual galaxy behavior, they struggle to account simultaneously for gravitational lensing, cluster dynamics, and the cosmic microwave background. Dark matter, despite being invisible, remains the most consistent explanation across multiple lines of evidence. Still, the conversation continues. The beauty of science lies not in certainty, but in testability. Every hypothesis must confront observation. Every model must align with data. As you listen quietly, it may seem remarkable that so much of reality remains unconfirmed. But uncertainty does not imply ignorance. It signals active exploration. It means we are looking carefully at the boundaries of knowledge, probing where our understanding fades into possibility. The universe does not reveal its structure all at once. It offers clues, rotational speeds, lensing distortions, background radiation patterns like soft footprints across space and time. Whether dark matter turns out to be a new particle, a hidden sector, a field, or something entirely unforeseen, its discovery would reshape physics. It would extend the standard model, redefine our inventory of matter, and perhaps illuminate connections between cosmology and quantum theory. And as we continue forward, another question gently arises. If most of the universe is invisible, what does that mean for how we define reality itself?
If most of the universe is invisible, then what we call normal may simply be what we are accustomed to seeing. The atoms that form your body, the air around you, the distant stars overhead, all of it belongs to a small minority of cosmic substance. Familiar does not mean fundamental, it only means illuminated. For centuries, humanity assumed that what was visible represented the whole. The sky appeared fixed and orderly. The earth seemed central. Matter felt solid and continuous. Each time we looked deeper, those assumptions softened. We discovered that Earth orbits the sun, that stars are distant suns, that atoms are mostly empty space, that particles behave as both waves and matter. Now, once again, the universe gently shifts our perspective. If dark matter and dark energy together make up roughly 95% of the cosmos, then the luminous universe is more like a thin surface layer, a bright shoreline outlining a vast, unseen ocean. Galaxies become islands of light floating within a sea whose properties we are only beginning to map. This realization does not diminish the visible universe. Instead, it deepens it. Every star becomes evidence of hidden structure. Every galaxy rotation curve becomes a clue. Every measurement of expansion becomes a dialogue between light and shadow. It also reshapes philosophical questions. What does it mean to say we understand reality if most of it lies beyond direct detection? Our knowledge becomes layered. We understand how dark matter behaves gravitationally, even if we do not know its composition. We can measure dark energy's influence on expansion, even if its origin remains unclear. Science often advances in this way, describing effects before uncovering causes. Electricity was harnessed before electrons were fully understood. Nuclear energy was released before quarks were identified. In each case, observation led theory, and theory gradually revealed deeper structure. Perhaps dark matter and dark energy represent the next layer in that unfolding story. There is something quietly comforting about this. The universe is not static, it is not finished. It continues to invite inquiry. The night sky above you is not only beautiful, it is active with unanswered questions, each one guiding future exploration. And as we move forward, another subtle realization begins to form. These mysteries are not distant in the sense of being irrelevant. The gravitational field that binds your galaxy, the expansion that shapes cosmic history, all of it operates continuously, even now. You are not separate from this story. You are part of a universe whose deepest ingredients remain unknown, resting quietly within structures shaped by forces we are still learning to name. As we continue this quiet journey, it helps to pause and consider just how extraordinary our current moment in cosmic history truly is. The universe is about 13.8 billion years old. For most of that vast span of time, there were no planets, no oceans, no living observers wondering about invisible matter. The first stars took hundreds of millions of years to ignite. Galaxies slowly assembled, merging and reshaping themselves over billions of years. Heavy elements, the carbon, oxygen, and iron that make life possible, were forged inside stellar cores and scattered through space by exploding stars. Everything familiar to us is the result of an extended cosmic evolution. And yet, we find ourselves living at a time when the universe is old enough to have developed complex structures, but not so old that its distant past has completely faded from view. We can still detect the faint cosmic microwave background. We can still observe galaxies billions of light years away. We can measure expansion across immense scales. This window will not remain open forever. If dark energy continues driving accelerated expansion, distant galaxies will eventually slip beyond the cosmic horizon. Their light will stretch and fade, redshifting into invisibility. Future observers, trillions of years from now, may see only their local cluster of stars, unaware of the broader cosmic web that once surrounded them. In that distant era, the evidence for the Big Bang might be far harder to detect. The afterglow radiation will have cooled and diluted even further. The large-scale structure will appear sparse and isolated. But right now, the universe is still richly observable. Its history is written in accessible light. Its structure can be mapped in detail. Its expansion can be measured. This coincidence that we exist at a time when the cosmos is both mature and still revealing has led some thinkers to reflect on the delicate balance of cosmic conditions. Why does dark energy dominate now rather than far earlier or far later? Why do matter and dark energy densities appear comparable in our era? Some suggest that this is simply how the universe unfolded. Others explore deeper explanations involving multiverse theories or anthropic reasoning, the idea that only certain cosmic conditions allow observers to arise and ask these questions in the first place. These ideas remain speculative, but they remind us that cosmology touches both physics and philosophy. As you rest quietly, consider this. The night sky above you is not just a backdrop. It is a snapshot taken at a uniquely informative moment in cosmic history. We are witnesses in a transitional age between matter's early dominance and dark energy's far future rule. And in this narrow window, we are learning to read the subtle handwriting of the universe itself.
The more we study the cosmos, the more we realize that its deepest mysteries do not shout, they whisper. Dark matter does not blaze across the sky. Dark energy does not ripple visibly through space. Instead, both reveal themselves through patterns, through motion, through subtle shifts in light. They are known by their influence, not by their appearance. This changes the way science operates at the largest scales. In a laboratory, you can isolate a particle, collide it, measure its properties directly. But in cosmology, the laboratory is the universe itself. We cannot manipulate galaxies or adjust expansion rates. We observe patiently. We measure carefully. We infer gently. Every rotation curve of a galaxy is a quiet clue. Every gravitational lens distortion is a trace of unseen mass. Every supernova brightness measurement is a data point in the story of cosmic acceleration. And as these clues accumulate, they form a coherent, if incomplete, picture. One of the most remarkable tools in this effort is simulation. Using powerful computers, scientists recreate virtual universes governed by the known laws of physics. They input the proportions of dark matter, dark energy, and ordinary matter, suggested by observation. Then they allow the simulation to evolve over billions of years of virtual time. When dark matter is included, the resulting structures resemble what we see through telescopes: the intricate cosmic web, the clustering of galaxies, the large voids between filaments.
When it is excluded, the structures fail to match reality. In this way, theory and observation meet in digital space. The invisible becomes testable, not through direct detection, but through consistency across scales. Yet the simulation is only as good as its assumptions, and assumptions evolve. New data refine them. Small discrepancies prompt adjustments. This is the quiet rhythm of scientific progress. Meanwhile, new observatories are coming online. Space telescopes designed to measure weak gravitational lensing with unprecedented precision. Ground-based surveys mapping billions of galaxies. Experiments listening for the faintest hints of particle interactions. Each instrument adds resolution to the cosmic portrait. It is easy to imagine that we stand near the end of discovery, having mapped the sky so extensively. But in truth, we may be closer to the beginning. The recognition that most of reality is invisible suggests that our inventory of nature is incomplete. The luminous universe, beautiful as it is, may be only a small sample of a far richer whole. And as we continue this gentle exploration, one possibility begins to shimmer at the edge of thought. What if understanding dark matter and dark energy does more than fill gaps in cosmology? What if it transforms our understanding of physics itself?
If dark matter and dark energy truly lie outside our current framework of physics, then their discovery would not simply add new entries to a cosmic inventory. It would reshape the foundation itself. The Standard Model of particle physics is one of the most successful theories ever developed. It describes quarks, electrons, neutrinos, and the forces that govern their interactions with extraordinary precision. Its predictions have been confirmed again and again in experiments. And yet this powerful framework contains no particle that clearly accounts for dark matter. Nor does it explain the origin of dark energy. This absence is striking. It suggests that the physics we know, as accurate and elegant as it is, may represent only part of a deeper structure. Just as classical mechanics was expanded by relativity and quantum theory, our current models may require extension. One possibility is supersymmetry, a theory proposing that each known particle has a heavier partner. Some of these partner particles could be stable and electrically neutral, ideal candidates for dark matter. For years, physicists hoped that high-energy collisions in particle accelerators would reveal evidence of such particles. So far, however, clear signals have not appeared. That does not mean supersymmetry is ruled out. It may exist at energy scales beyond current reach. Or nature may have chosen a different path altogether. Other theoretical frameworks explore entirely new fields and symmetries, hidden sectors that barely interact with familiar matter. Some suggest that dark matter could be connected to the early inflationary expansion of the universe. Others investigate whether dark energy might emerge naturally from quantum gravity, a still incomplete theory attempting to unify general relativity with quantum mechanics. What makes this moment in science so compelling is the convergence of mysteries. The smallest scales, governed by quantum fields, and the largest scales, governed by cosmic expansion, may be linked. Dark energy involves the energy of empty space. Dark matter influences structure formation across billions of light years. Both challenge our understanding of fundamental laws. In physics, revolutions often begin with inconsistencies. A calculation that does not match observation, a prediction that fails, a measurement that refuses to align with expectation.
And so dark matter and dark energy represent persistent inconsistencies, not chaotic ones, but precise and measurable deviations from what visible matter alone would produce. And so the search continues, not only through telescopes pointed outward, but through equations written on chalkboards and simulations running quietly in laboratories. Somewhere within this intersection of theory and observation, a clearer picture may emerge. Until then, the universe remains partially veiled, luminous at the surface, profound in its depths, inviting us to keep looking, to keep listening, and to remain patient with mysteries that unfold slowly across time. As we move deeper into this quiet exploration, it becomes clear that dark matter and dark energy are not isolated puzzles. They are threads woven into nearly every major question in modern cosmology. Consider black holes, for example. These regions of extreme gravity form when massive stars collapse or when enormous amounts of matter gather at galactic centers. At the heart of nearly every large galaxy lies a supermassive black hole, millions or even billions of times the mass of our Sun. Their formation and growth are closely tied to the evolution of galaxies themselves. Dark matter halos provide the gravitational environments in which galaxies form. Without those halos, the gas that fuels star formation and black hole growth might never have condensed in the first place. In this way, even the most extreme objects in the universe may owe their existence to something invisible. Then there is the question of cosmic inflation, the brief, rapid expansion believed to have occurred fractions of a second after the Big Bang. Inflation explains why the universe appears so uniform on large scales and why tiny fluctuations existed to seed later structure. Some theories suggest that the same kind of fields responsible for inflation might be connected in some distant way to dark energy today. These connections remain speculative, but they hint at a deeper unity. The forces shaping the earliest moments of time may still influence the cosmos now. Even neutrinos, those nearly massless particles that stream through space by the trillions, play a subtle role in cosmic evolution. Their tiny masses affect how structure forms on large scales. Precise measurements of galaxy clustering can, in fact, constrain neutrino properties. In this way, cosmology and particle physics intertwine. It is remarkable how much we have learned from light alone. Photons carry information across billions of years. By studying their spectra, polarization, and redshift, we reconstruct histories we never witnessed directly. The universe becomes an archive, its pages written in radiation. And yet light tells only part of the story. Dark matter does not shine. Dark energy does not glow. Gravitational waves ripple through space almost imperceptibly. There may be entire layers of reality that reveal themselves only indirectly, through subtle influence rather than direct emission. This realization encourages humility. It reminds us that perception is not equivalent to completeness. The senses, even when extended by telescopes and detectors, provide only a filtered glimpse of what exists. But humility does not weaken discovery, it strengthens it. Each unanswered question sharpens inquiry. Each mystery refines our tools. The absence of direct detection does not close doors, it opens new directions. As the universe continues expanding quietly beyond your window tonight, it carries with it unanswered questions, steady, patient, and waiting for careful minds to unravel them. And somewhere within those questions lies the possibility that our current understanding is only the beginning. There is something quietly beautiful about the idea that the universe is still unfinished in our understanding. Not incomplete in its structure, but incomplete in our awareness of it. For a long time, humanity believed the cosmos was simple and static. The stars were thought to be fixed points embedded in an eternal sky. Then we discovered galaxies beyond our own. Then we discovered expansion. Then we discovered that expansion is accelerating. Each layer revealed something deeper, and each revelation gently unsettled what came before. Dark matter and dark energy continue that pattern. They remind us that even when equations appear elegant and observations precise, there may be unseen variables shaping the outcome. The universe does not owe us simplicity. It unfolds according to principles we are still uncovering. And yet, there is a kind of calm in that realization. The fact that most of reality remains invisible does not make it chaotic. On the contrary, the large-scale universe behaves with extraordinary order. Galaxies rotate in predictable ways. Clusters follow gravitational laws. Expansion follows measurable trends. The hidden components may be unknown in composition, but their effects are consistent and mathematically coherent. This suggests that the underlying rules, though incomplete in our models, are not random. Perhaps one day, dark matter will be identified as a specific particle detected in a laboratory after decades of silence. Perhaps dark energy will be understood as a property emerging naturally from a deeper quantum theory of gravity. Or perhaps the true explanation will surprise us entirely, something elegant that reframes both mysteries at once. History offers perspective here. Before the discovery of atoms, matter was mysterious. Before electromagnetism was unified, electricity and magnetism seemed unrelated. Before relativity, space and time were thought to be separate absolutes. Each breakthrough required patience, years, sometimes generations, of careful thought and incremental progress. We may be living in a similar transitional era now, aware of the outline of something vast, but not yet seeing its inner structure clearly. As you rest in the stillness of this night, imagine the universe continuing its quiet expansion, galaxies drifting farther apart, dark matter halos holding structures gently in place, dark energy stretching the fabric of space with steady persistence. Nothing dramatic, no sudden shifts, just gradual, immense processes unfolding over billions of years. And within that vastness, a small planet orbiting an ordinary star has produced minds capable of asking these questions. That too is part of the mystery. We are not separate from the cosmos we study. We are one of its ways of becoming aware of itself, even if much of it still lies beyond the light we can see.
If we step back even further, beyond particles and expansion rates, another gentle question begins to form. Why does the universe allow itself to be understood at all? The laws governing gravity, motion, and energy are written in mathematical language. Equations describe how galaxies rotate, how light bends, how space expands. These equations are not arbitrary. They reflect consistent patterns woven into reality itself. Even when we do not fully grasp the underlying ingredients, the patterns remain steady. Dark matter follows gravitational rules with remarkable reliability. Dark energy influences expansion in a measurable, almost serene way. The cosmos behaves as though it is guided by principles that are subtle yet coherent. There is a quiet elegance in that. For centuries, scientists have trusted that careful observation combined with mathematical reasoning can uncover deeper layers of truth. And so far, that trust has been rewarded.
Each time we refine our instruments or improve our calculations, the universe responds with consistency. It does not contradict itself without reason. It does not behave chaotically on large scales. Instead, it invites interpretation. This does not mean every mystery will be solved easily. Some may require technologies not yet invented. Others may demand new theoretical frameworks that challenge our intuitions. But the very existence of measurable structure, of patterns in galactic motion, of statistical regularities in background radiation, suggests that the hidden components of the universe are not beyond comprehension forever. They are simply waiting for clearer insight. Meanwhile, our understanding continues to expand alongside the cosmos itself. Each generation inherits data from the previous one, refining it, questioning it, testing it again. Science becomes a long conversation across time, a gradual sharpening of focus. Dark matter once seemed speculative. Now it is a central pillar of cosmology, even if its nature remains unknown. Dark energy was once unimaginable. Now it shapes every model of cosmic fate. And perhaps future observers will look back at this era as the early stage of a larger revelation, the moment when humanity recognized that most of existence lies beyond direct sight. As the night deepens and the stars continue their silent glow, consider how extraordinary it is that we can trace their motions, measure their distances, and infer the invisible structures around them. The universe does not simply exist, it communicates through patterns. And in listening carefully to those patterns, we draw closer, slowly, patiently, to understanding a reality far greater than the light that first caught our eyes.
As we follow these patterns deeper, another realization begins to settle gently into place. The universe is not only vast in space, but vast in time. When you look at a distant galaxy, you are not seeing it as it is now. You are seeing it as it was, millions or even billions of years ago. Light carries history. Every photon that reaches us is a messenger from the past. In this way, astronomy becomes a kind of time travel, not through machines, but through observation. Dark matter and dark energy are woven into this history at every stage. In the early universe, dark matter helped small fluctuations grow into the first gravitational structures. Later, it guided the formation of galaxies and clusters. Much later still, dark energy began to dominate, gradually accelerating the expansion of space and altering the long-term trajectory of cosmic evolution. These influences are not abrupt. They unfold across immense stretches of time, millions, billions, trillions of years. From a human perspective, such scales are almost impossible to grasp. Civilizations rise and fall in mere thousands of years. Stars live for billions. Galaxies evolve over tens of billions. The universe itself measures its life in even grander spans. And yet, despite this immensity, we can detect subtle transitions. We can identify the moment when matter stopped dominating cosmic expansion and dark energy began to lead. We can calculate when the first atoms formed. We can estimate when the first stars ignited. These milestones form a quiet timeline, stretching from the hot beginnings of the cosmos to the cool vastness we observe today. Looking ahead, the timeline continues.
If dark energy remains constant, expansion will persist indefinitely. Distant galaxies will fade from view. Star formation will gradually slow as gas is consumed. Over trillions of years, stellar remnants will dominate. Black holes will slowly evaporate through faint quantum processes. The universe will grow colder and darker. But these possibilities lie in unimaginably far in the future. For now, we inhabit an era rich with structure and light. Galaxies shine, new stars are born. Observers can look outward and reconstruct cosmic history. There is something profoundly peaceful about recognizing this long arc of time. The universe is not rushing. Its processes unfold with patient consistency. Even acceleration itself is gradual, measured in kilometers per second per megaparsec, not in sudden leaps. As you rest quietly, imagine space expanding gently around you, not violently, not dramatically, but steadily, increasing the distances between distant galaxies in imperceptible amounts. The night sky appears still, but it is part of an ever-evolving story, and within that story, dark matter and dark energy remain the silent protagonists, shaping beginnings, guiding transitions, and defining the far future of everything that exists.
There is a quiet irony in the fact that the most dominant ingredients of the universe are the least understood. For centuries, science progressed by studying what could be directly observed: the motion of planets, the spectrum of starlight, the behavior of falling objects. Even when atoms were invisible, their effects were measurable in chemistry and thermodynamics. Step by step, the unseen became familiar. But dark matter and dark energy present a different kind of challenge. They are not hidden in small scales like atoms once were. They dominate the largest scales imaginable. They shape galaxy clusters, influence cosmic expansion, and determine the overall geometry of the universe. And yet, they remain elusive. Part of the reason lies in how gently they interact. Dark matter does not emit light. It does not absorb or reflect photons. If it passes through ordinary matter, it does so almost silently. Its presence is inferred only through gravity, through motion that deviates ever so slightly from expectation. Dark energy is subtler still. It does not gather into halos or clumps. It does not form structures. Its influence becomes noticeable only across billions of light years, revealed in the gradual acceleration of space itself. This means that our understanding depends on precision. Astronomers must measure distances with extraordinary care. They must calibrate brightness, account for dust, refine redshift data, and cross-check independent methods. Tiny uncertainties matter. A small miscalculation can ripple across cosmic scales. Yet despite these challenges, the evidence for both dark matter and dark energy is remarkably consistent. Independent techniques, galaxy rotation curves, gravitational lensing, cosmic background radiation patterns, supernova observations, all converge toward the same broad conclusion. The universe contains far more than meets the eye. And perhaps that is the deeper lesson. Reality is layered. What we perceive directly is only one stratum. Beneath it lie deeper structures, accessible not through sight alone, but through inference, mathematics, and patient observation. In a way, this mirrors other areas of science. The electromagnetic field cannot be seen directly, yet its effects are undeniable. The curvature of space-time cannot be touched, yet it governs motion. Dark matter and dark energy may simply represent the next layer in this unfolding pattern. Phenomena that feel mysterious now, but may one day seem as natural as gravity itself.
Until then, the night sky remains both familiar and profoundly strange. You can look up and see stars, constellations, the faint glow of distant galaxies, all while knowing that most of what exists between them and beyond them remains invisible. And in that quiet knowledge, the universe feels larger still.
As we draw further into this quiet contemplation, it becomes clear that mystery is not a flaw in our understanding. It is a natural stage within it. Dark matter and dark energy do not signal failure, they signal depth. They remind us that knowledge expands in layers and that each solved question often reveals a broader horizon beyond it. There was a time when the Milky Way was thought to be the entire universe. Then we discovered other galaxies. There was a time when the universe itself was thought to be static. Then we discovered expansion. Each shift widened our sense of scale. Now we stand at another widening. We know the proportions of the cosmos with surprising precision, roughly 5% ordinary matter, about 27% dark matter, nearly 68% dark energy. These numbers are not guesses. They arise from careful measurement of cosmic background radiation, galaxy clustering, and large-scale structure. And yet, knowing the proportions does not mean knowing the substance. It is as if we have weighed the universe, mapped its outline, traced its evolution, and still lack the recipe. This situation may feel unsettling at first, but there is something deeply peaceful about it as well. The universe is not exhausted. It is not fully cataloged. It continues to offer puzzles worthy of generations. As you rest here in the stillness, consider how extraordinary it is that a species on a small planet can measure the expansion of space itself, that we can infer invisible halos around galaxies billions of light years away, that we can reconstruct events from nearly 14 billion years ago using faint background radiation. The scale is immense, and yet the method is simple. Observe carefully, think clearly, test patiently. The night sky above you appears calm and unchanged, but within it, galaxies are orbiting, merging, drifting. Space is stretching quietly. Dark matter is shaping structure. Dark energy is guiding destiny. Nothing announces these processes. They unfold with steady consistency. And perhaps that is the most soothing realization of all. The universe is vast, mostly unseen, and still partially mysterious, yet it behaves with remarkable order. Its hidden components do not introduce chaos, they deepen coherence. As we continue forward, the questions remain open. What is dark matter made of? What is the true nature of dark energy? Will they one day fit seamlessly into a broader theory of reality? For now, the answers rest just beyond reach. But the search itself, calm, persistent, and curious, is part of the universe's unfolding story. As we continue drifting through these questions, it becomes clear that the mystery of the universe is not loud or urgent. It is slow, expansive, patient. Dark matter does not rush to reveal itself. Dark energy does not surge dramatically through space. Their influence is measured across billions of years and unimaginable distances. To study them requires a similar patience, a willingness to think in cosmic timescales rather than human ones.
And yet, despite these immense scales, the clues are accessible. The rotation of a galaxy can be measured by observing the shift in the light of its stars. The expansion of space can be inferred from the stretching of distant light waves. The distribution of dark matter can be mapped by studying tiny distortions in background galaxies. It is almost astonishing that such delicate measurements allow us to reconstruct such vast structures. When we look at the cosmic microwave background, the faint afterglow of the early universe, we are seeing a map of tiny temperature variations. Those slight fluctuations, smaller than a fraction of a degree, contain within them the blueprint of everything that would follow. From those small irregularities grew galaxies, stars, planets, and eventually observers. Dark matter amplified those initial differences. Dark energy now governs their separation. The story is cohesive, even if incomplete, and perhaps the incompleteness is part of its beauty. If every mystery were already solved, the universe would feel smaller. Finality would replace curiosity. But instead, there remains space, intellectual space, for discovery. New telescopes are being built, new detectors are being refined, new theories are being tested. Each one represents a quiet extension of human awareness into regions once thought unreachable. It is possible that in the coming decades a breakthrough will occur. A detector may register a clear signal of a dark matter particle. Observations may reveal subtle evolution in dark energy. A new theoretical framework may unify gravity and quantum mechanics in an unexpected way. Or progress may continue gradually through small refinements and careful exclusions. Either way, the process itself reflects something profound. The universe is not separate from the minds studying it. The same physical laws that govern galaxies also govern neurons. The same atoms forged in ancient stars form the instruments we use to measure starlight. In contemplating dark matter and dark energy, the cosmos is, in a sense, reflecting upon its own hidden structure. And as the night remains still outside, that quiet reflection continues, steady, expansive, and full of possibility. There is another gentle layer to this story, one that moves beyond equations and observations and into perspective. When we say that most of the universe is invisible, it can sound dramatic. But invisibility does not mean absence. It simply means that our senses, even when extended by telescopes and detectors, capture only certain forms of interaction. Light is just one messenger among many. For most of human history, we could not see radio waves, X-rays, or infrared light. They were always present, but unnoticed. Only when instruments were developed did those hidden layers become visible. The sky transformed. Familiar constellations took on new forms when observed in different wavelengths. It is possible that dark matter and dark energy represent similar frontiers, aspects of reality that require new modes of detection. Already, gravitational waves have opened a new window. These ripples in space-time, first directly detected in recent years, allow us to observe cosmic events that produce little or no light. Black hole mergers, for example, can now be heard through space-time vibrations. This breakthrough reminds us that the universe communicates in more than one way. Perhaps future instruments will detect subtle interactions of dark matter beyond gravity. Perhaps quantum experiments will reveal tiny signatures of vacuum energy connected to dark energy. Each technological advance reshapes what is observable. Meanwhile, theoretical work continues quietly. Physicists explore connections between dark energy and the geometry of space-time. They examine whether the acceleration of expansion could emerge naturally from deeper gravitational principles. Some investigate whether information itself plays a fundamental role in cosmic structure. These explorations may sound abstract, but abstraction has often preceded clarity. Maxwell's equations once seemed purely mathematical. Now they describe the behavior of light and electricity. Einstein's curvature of space-time once felt theoretical. Now it guides satellite navigation. In time, what feels mysterious may feel inevitable. For now, the universe retains its layered nature. Stars shine brightly, while dark matter shapes their motion invisibly. Space expands silently under the influence of dark energy. The cosmic web stretches across distances too vast to imagine fully. And yet none of this disrupts the calm of the night sky. The stars appear steady, the constellations familiar, the darkness between them deep. Perhaps that is the most soothing aspect of all. Even in a universe dominated by unseen forces, the overall structure remains harmonious. Motion follows law, expansion follows pattern. Gravity curves space with quiet consistency. Mystery does not imply disorder. It simply invites us to look more carefully and to accept that understanding unfolds gradually, like light traveling across billions of years to reach us at last. As we continue reflecting on these unseen forces, another subtle truth begins to emerge. Scale changes everything. On human scales, gravity feels simple. It keeps our feet on the ground, it governs the motion of the moon, it shapes the orbits of planets. But on galactic scales, gravity behaves in ways that reveal the presence of dark matter. On cosmic scales, across billions of light years, expansion reveals the influence of dark energy. The same fundamental laws operate everywhere, yet their effects become more nuanced as the scale increases. Imagine shrinking yourself down to the size of an atom. You would see mostly empty space, with tiny particles bound together by forces far stronger than gravity. Now imagine expanding outward beyond galaxies. You would see enormous regions of near emptiness, with galaxies tracing delicate threads across the void. Dark matter dominates in those vast regions, providing the gravitational glue that binds clusters and filaments. Dark energy dominates on even larger scales, gradually increasing the distance between those structures. What is fascinating is how balanced the universe appears. If dark matter were significantly weaker, galaxies might not have formed as efficiently. If dark energy were much stronger early on, structure might have been torn apart before stars could ignite. If gravity behaved differently at large distances, the cosmic web might never have taken shape. This does not necessarily imply intention or design, only sensitivity. The large-scale behavior of the universe depends delicately on the interplay of its components. And yet, from our small vantage point, everything feels steady. The Earth rotates calmly, the sun rises and sets, the stars appear fixed. We do not sense the expansion of space because it unfolds on scales far beyond everyday experience. The distances between galaxies increase, but the forces binding local systems, stars within galaxies, planets around stars, remain strong enough to resist that expansion. In this way, the cosmic and the local coexist peacefully. Dark energy stretches the universe as a whole, but it does not pull apart atoms or disrupt planetary orbits. Dark matter shapes galaxies, but it does not interfere with daily life. These immense forces operate at levels that are both fundamental and distant. There is comfort in that layered structure. The universe can be vast and mysterious without being chaotic. It can be dominated by unseen components without destabilizing the familiar world we inhabit. As you rest beneath the quiet sky, remember that the stars above are part of a much larger architecture, one built by gravity, shaped by dark matter, and carried outward by dark energy. The calm you feel is not separate from that architecture. It is a small, local stillness within a universe that moves slowly, consistently, and with profound depth. As our journey continues, it becomes clear that one of the most remarkable aspects of the universe is not just its size or mystery, but its continuity. From the smallest quantum fluctuations to the largest cosmic structures, there is a thread of connection. Tiny variations in density in the early universe eventually became galaxies. Subtle differences in energy density now influence the acceleration of expansion. What begins as a whisper in the fabric of space-time can grow into something vast. Dark matter played its role early, amplifying minute irregularities. Dark energy plays its role later, shaping the grand trajectory of cosmic history. Neither interrupts the other abruptly. Instead, they operate in sequence, like chapters in a long and unfolding narrative. We often imagine cosmic events as dramatic and explosive, and certainly there are supernovae, black hole mergers, and powerful bursts of radiation. But the deeper forces guiding the universe are gentle. Gravity accumulates matter slowly. Expansion stretches space steadily. Dark energy accelerates with quiet persistence. The grand story of the cosmos is not written in sudden leaps, but in gradual transformation. This perspective invites a certain calm. The universe is not racing toward chaos, it is evolving according to principles that remain consistent across time and distance. Even when we do not fully understand those principles, we can observe their coherence. Think again of the cosmic microwave background, that faint glow from the early universe. Within its tiny temperature variations lies a map of future structure. Those variations were minuscule, yet they shaped everything that followed. Dark matter amplified them. Gravity refined them, stars emerged, galaxies assembled. Billions of years later, observers evolved who could measure those same fluctuations and reconstruct the story. There is something deeply elegant in that loop. The early universe leaves traces, the later universe deciphers them. The same physical laws guide both stages. Dark energy, though mysterious, also fits within this continuity. Its influence becomes stronger as space expands, yet it does so smoothly. There is no sharp boundary where matter suddenly ceases to matter. Instead, there is a gradual transition, a shift in dominance over cosmic time. And perhaps that is the lesson hidden beneath the equations. Mystery does not break continuity. It simply reveals that continuity extends deeper than we expected. As the night stretches on and the stars remain steady overhead, remember that they are part of a story still unfolding, a story shaped by forces both seen and unseen, unfolding with patience across unimaginable spans. We are listening to that story now, not at its end, but somewhere along its quiet, expansive middle. At this point in our quiet exploration, it may feel as though we have traveled very far, from spinning galaxies to the earliest light of the universe, from invisible halos to the accelerating stretch of space itself. And yet, in another sense, we have only traced the outline. There is still a deeper question beneath all of this. Why does the universe have the particular ingredients it does? Why is there dark matter at all? Why does space possess energy? Why do the constants of physics take the values we measure? These are not easy questions. They move beyond observation and into the foundations of theory. Some physicists explore the possibility that our universe is one of many, each with different physical parameters. In such scenarios, the values we observe may not be unique, but simply the ones compatible with long-lived structure and complexity. Others search for a more unified explanation, a theory in which both dark matter and dark energy arise naturally from deeper symmetries. Perhaps both are manifestations of a single underlying principle not yet recognized. Throughout scientific history, apparent separations have often dissolved into unity. Electricity and magnetism were once distinct phenomena. Later, they became aspects of a single electromagnetic field. Space and time were once separate. Relativity joined them into space-time. It is possible that dark matter and dark energy, though different in behavior, share a deeper connection. Or perhaps they are entirely separate, two independent features of reality that simply coexist. For now, the universe does not answer directly. It offers data. It offers consistency. It offers patterns that guide theory but do not fully resolve it. And perhaps there is a quiet wisdom in that. A fully solved universe might feel smaller. A completely mapped cosmos might leave little room for curiosity. Instead, we inhabit a reality that reveals much, yet retains depth. The night sky, which appears calm and unchanging, is part of a vast dynamic system shaped by ingredients we cannot see. Every star is embedded in dark matter. Every distant galaxy drifts under the influence of dark energy. And still, from our vantage point, there is stillness. You can look upward and feel peace, even knowing that space itself is expanding. You can rest quietly, even knowing that most of the universe is invisible. The mysteries do not diminish the calm, they deepen it. They remind us that reality is larger than perception, and that understanding unfolds slowly, like starlight crossing immense distances, arriving gently in moments like this one. As we move closer to the horizon of our journey, it becomes clear that the greatest mysteries of the universe are not barriers, they are invitations. Dark matter invites us to look beyond light. Dark energy invites us to rethink space itself. Both encourage us to expand our definitions of what is real. For much of history, reality was defined by what could be seen and touched. Then, microscopes revealed cells, telescopes revealed galaxies, particle accelerators revealed quarks. Each expansion of perception widened the boundary of existence. Now, with dark matter and dark energy, that boundary stretches again. We accept that most of the universe is composed of something invisible. We accept that empty space carries energy. We accept that expansion can accelerate. These ideas would have seemed almost poetic centuries ago. Today, they are supported by data. And yet, there is something poetic about them still. The idea that galaxies float within unseen halos, that the fabric of space itself quietly stretches, that the cosmos is mostly hidden yet profoundly ordered. There is beauty in that paradox. The visible universe, stars, nebulae, galaxies, is like the illuminated crest of a wave. Beneath it lies depth, immense, quiet depth, and we are only beginning to explore it. Future generations may look back at this era as the beginning of a deeper understanding, the time when humanity recognized that the familiar 5% was only the surface. They may develop new physics that makes dark matter as ordinary as electrons and dark energy as natural as gravity. Or they may discover something even more unexpected, a new framework that reframes everything we currently assume. For now, though, the mystery remains steady and patient. The night sky does not rush us toward answers. It simply exists, vast, silent, and layered. Dark matter continues holding galaxies together. Dark energy continues guiding expansion. Stars continue shining across immense distances. And here, on a small planet orbiting an ordinary star, observers continue asking quiet questions. There is something deeply comforting in that continuity. The universe unfolds according to principles that may not yet be fully understood, but they are consistent, measurable, and profound. As you rest in this stillness, remember that you are part of this unfolding, a small but conscious fragment of a cosmos that is still revealing itself. And the story is not finished. It is still expanding.
If we pause here, near the quiet edge of what we currently understand, a gentle awareness begins to settle. The universe is not only vast, it is subtle. Its greatest influences are not always the brightest or the loudest. Dark matter does not glow. Dark energy does not flash, and yet together they determine the structure and fate of nearly everything we see. There is something profoundly humbling in that realization. For thousands of years, humanity studied the heavens with the naked eye. Constellations were drawn, myths were told. The stars felt like fixed lights set into a distant dome. Slowly, instruments extended our reach. Telescopes revealed depth. Spectroscopy revealed composition. Space probes revealed planetary surfaces. And now, we find ourselves confronting the idea that even all of that luminous knowledge describes only a small fraction of reality. The visible universe is like the surface of a calm sea at night. We can see the reflections, the faint glimmers, the patterns of light. But beneath the surface lies depth, quiet, expansive, and largely unseen. Dark matter forms the unseen currents that guide the motion of galaxies. Dark energy acts like a slow, steady tide, drawing distant shores farther apart. Neither disrupts the calm appearance of the sky. Instead, they operate beneath perception, shaping outcomes across unimaginable distances.
perhaps that is why the night feels peaceful despite its complexity. The cosmos is not chaotic, it is layered. The laws that govern it remain consistent. Gravity curves space-time with quiet precision. Light travels at a constant speed. Expansion follows measurable patterns. Even the unknown components behave predictably in their effects. Mystery, in this sense, is not disorder. It is depth awaiting clarity. As we approach the final stretches of this reflection, the questions remain open, but they no longer feel urgent. They feel steady, patient. What is dark matter made of? What truly drives cosmic acceleration? Will a future theory weave these elements together into a single elegant explanation? The answers may come slowly, over decades or centuries. But tonight, under a sky filled with ancient light, it is enough to recognize that we live inside a universe far richer than what first meets the eye. A universe mostly invisible, yet beautifully coherent. And in that awareness, there is calm. As we near the end of this long, quiet reflection, one final perspective begins to take shape. Everything we have discussed, dark matter, dark energy, cosmic expansion, the formation of galaxies, unfolds without haste. The universe does not strain toward completion. It evolves with patience measured in billions of years. From our human viewpoint, this can feel overwhelming, but when we slow down and simply observe, the vastness becomes soothing rather than intimidating. Dark matter holds galaxies together with steady gravity. Dark energy stretches space with gentle persistence. Stars burn for millions to billions of years, radiating light into expanding darkness. Nothing in this process is frantic. Even acceleration, the very idea that the universe is speeding up, occurs gradually, almost imperceptibly. Distances between distant galaxies increase by small amounts over immense stretches of time. The change is real, but it is not abrupt. In that sense, the cosmos models a kind of calm consistency. It reminds us that large transformations can happen slowly, that profound shifts do not always require noise, that expansion can be quiet. There is also something deeply grounding about recognizing how small we are within this framework, not insignificant, but local. The expansion of the universe does not pull apart our solar system. Dark matter halos do not disturb daily life. These immense forces operate on scales far beyond our immediate experience. The Earth remains stable in its orbit. The Sun continues its steady fusion. The constellations rise and set. And yet all of this exists within a universe mostly composed of unseen ingredients. That paradox, visible calm within invisible depth, is one of the most beautiful features of reality. Perhaps understanding does not always require complete answers. Sometimes it requires acceptance of scale, acceptance that some layers of existence are still unfolding in our awareness. The night sky above you carries ancient light. It also carries unanswered questions. Both coexist peacefully. As space continues expanding and galaxies drift along their invisible scaffolds, we remain here, observers in a brief but meaningful chapter of cosmic history. And maybe that is enough. To know that the universe is vast, layered, and still partially mysterious, yet orderly, measurable, and profoundly consistent. A quiet cosmos, mostly unseen, continuing its slow and steady expansion into the depths of time. As our journey gently approaches its final horizon, there is one more thought worth resting with. For all its vastness and invisibility, the universe is remarkably knowable. Not completely, not yet, but meaningfully. We can calculate how much dark matter must surround a galaxy by watching how its stars move. We can measure the influence of dark energy by observing how distant supernovae fade. We can map the early universe by studying faint temperature patterns in ancient radiation. These are not guesses. They are careful inferences drawn from consistent patterns. This tells us something important. Even when the ingredients are hidden, the effects are traceable. Even when matter does not shine, gravity reveals it. Even when space itself carries energy, its influence leaves measurable fingerprints across time. The universe, though mostly unseen, is not inaccessible. There is a quiet partnership between mystery and measurement. Each unanswered question guides the next experiment. Each discrepancy refines the next theory. Each new telescope sharpens the image just a little more. And through this slow accumulation of insight, the outline of the invisible becomes clearer. Perhaps one day a detector will finally register the unmistakable signal of a dark matter particle. Perhaps future observations will reveal subtle changes in dark energy's behavior. Perhaps a new theory will weave gravity and quantum physics together into a deeper understanding. Or perhaps progress will continue gradually through steady refinement rather than dramatic breakthrough. Either way, the process itself is extraordinary. On a small planet orbiting an ordinary star, beings made of stardust have developed the ability to measure the expansion of space and infer the existence of dark matter across billions of light years. That alone is remarkable. As you rest in the quiet of this night, imagine the vast cosmic web stretching outward, galaxies resting in dark matter halos, separated by growing distances shaped by dark energy. The sky may appear still, but it is part of an unfolding story written across immense scales of space and time. And we are not outside that story. We are woven into it. A brief, conscious moment within a universe that is still expanding, still evolving, and still quietly revealing its deeper layers to those who choose to look up and wonder.
And now, as we reach the gentle close of this long reflection, everything settles into perspective. Above you, the night sky remains calm. The stars glow with steady light. Constellations hold their familiar shapes. Nothing appears unusual. Nothing announces that most of reality is invisible. And yet, quietly, galaxies are embedded in vast halos of dark matter. Quietly, space itself continues to expand under the influence of dark energy. Quietly, the cosmic web stretches across distances too large to truly imagine. The universe is not only larger than we once believed, it is deeper. What we see, stars, planets, nebulae, is only a small luminous layer resting upon unseen foundations. Dark matter provides the structure. Dark energy shapes the long-term destiny. Ordinary matter shines briefly in between. And still, the whole system remains astonishingly coherent.
Gravity follows its laws. Light travels faithfully across billions of years. Expansion unfolds with measurable consistency. Even the unknown components behave in ways that can be described, predicted, and studied. Mystery here does not mean chaos. It means there are chapters still unread. There is something profoundly peaceful about that idea. The cosmos is not finished revealing itself. It continues expanding, evolving, and quietly inviting curiosity. Perhaps in time, dark matter will no longer be dark. Perhaps dark energy will become a natural part of a broader theory. Perhaps the invisible will become understood, just as atoms and galaxies once were. But tonight, it is enough to rest in the awareness that we live inside something vast, layered, and still unfolding. The light reaching your eyes began its journey long ago. The galaxies it came from are drifting slowly outward. The invisible framework that holds them together remains present, silent, steady. And here you are, a small, conscious part of that immense story. The universe expands, galaxies turn, time moves forward. All of it guided by forces both seen and unseen. So as the night deepens and your thoughts grow quieter, imagine the cosmos continuing its calm expansion, not hurried, not chaotic, but patient. A vast, mostly invisible universe, steady, ordered, and beautiful.